Okay. Not coming through. You guys hear me? What? It's like not coming, right? Is it coming? Oh, okay. Weird. Try to put this a little higher. Okay, try to increase the volume. Okay. That's coming through now? Okay, good. Sweet. Okay, welcome back. Get started here. You're probably tired of seeing me and all these lectures the last few days. Professor Gonzalez has been busy writing the midterm, so it's looking good. You guys are gonna be okay. 1 week away. So a few announcements. Yeah, so homework 7 due next Wednesday, lab 6 due today, and then 1 week from the midterm. Check out this midterm prep post on Ed. Walks through the best way to get ready for the midterm. And it's pretty similar to what I shared in lecture like last time, but that's a good guideline to follow there. Yeah, any questions? Oh man, still not going? Is that better? Okay, this is, yeah, it's being weird today. I don't know. Like I could try this thing, which I've never used. Let's try it. Okay, better. Okay, I don't know how to do this. Let's do this thing, I guess. Okay, whoa, nice. All right, I guess I should just do this every time. Sweet. Okay, so yeah, that's announcements. Any questions about logistics? Okay. All right. So we are wrapping up this week with another example of hypothesis testing. So far, everything we've done has really been talking about the distribution of like a single population. So, you know, we've done stuff like, hey, these plants in the population have a 75% chance of being purple, or like this population of people in Alameda has this distribution of like ethnicities. So it's been talking about one population. And then even on Wednesday too, we were saying, hey, there's this like class, the stats class, and we have all these midterm scores. And then we're saying this one section's like a random sample from the entire class. Today, we're going to talk about how do you deal with a situation where you have like two populations. So what if I have data coming from two populations? Can I say anything about those two populations and how they relate to each other? So what we're going to look at today is a numerical example. So we're going to have two samples. They're both numerical data coming from some different populations. And what we're trying to assess is the underlying numerical data in those populations, is it the same or is it different? Can we say that one population has larger values on average than another? And so we're going to try to make that conclusion using statistics and data science. And we're going to try to do that just using these two samples that we observed. So very similar to what we've done so far, except now we have two samples rather than just one single set of data. Cool. So before we do that, quickly wanted to just recap some of the p-value stuff. Saw a lot of questions on Ed about this. It's a tough concept. And it's a little bit weird. So I just want to like answer any questions about that. But I think fundamentally p-value is an area. That's like the first thing you should remember. And really it's a very specific area of a histogram that's generated using the null distribution. So you're kind of assuming like the null hypothesis is true and the p-value is in the context of that. So the p-value doesn't really mean anything in any other context. Like it's not related really to the alternative hypothesis that much. It's more just, let's assume the null is true. Let's simulate a bunch of data, assuming the null is actually true. And then let's calculate an area with respect to that distribution. So it's all very specific to that. The only dependence on the alternative hypothesis is the direction in which you look to calculate the p-value. So basically you do your simulations, you have your observed value, which in this case is the red dot. And then you need to figure out, should I go to the left or to the right? What direction do I need to calculate the area? That is determined by the alternative hypothesis. And so the way to know that is back when you're going through those steps, you kind of write down your hypotheses, you come up with a test statistic. You should write down like high values of this test statistic equals alternative, low values equals the null. Like write that out very clearly so you know which direction you're going to look in. And then once you know that, maybe, you know, it depends on the problem. For some values, the test statistic being low is more evidence for the alternative. Some problems it's going to be high, it just depends on the context. And we went over a few examples last time. But once you have that figured out, just calculate the area in the direction of the alternative. That's pretty much it. And so in this particular case, this was that GSI example. Alternative was that like the scores are lower in this particular section beyond what could be explained by chance. So alternative is kind of going to be supported by test statistics that are low. And so that's why we calculate area to the left. So we know what our observed value is, and then we just look at how much of the histogram is to the left, and that's your p-value. And that's pretty much it. And then all you do is compare that p-value to a cutoff. And so usually we'll use 5% as the cutoff. Sometimes we'll use 1%. This will be given to you explicitly in the problem. And in actual practice, it just varies by domain. Some domains have, maybe like a higher standard for some reason. Like, let's say you're in the medical community, maybe you'd be using a 1% cutoff because like it could actually affect people's lives. Whereas if it's an example where it's maybe not as sensitive, it's more just you're trying to understand something, then maybe a 5% cutoff's okay. So it really just depends on the context. But those are the numbers you'll like typically see here. The lower the p-value, the more evidence there is for the alternative. So it sounds a bit weird, but maybe you should think of it the other way, which is like higher p-values is evidence for the model, because higher p-values means observed data is like fairly consistent with the model. It's something that we would expect to see just by chance. If it's a low value, it means what we observed is something very rare and not something we'd expect to see by chance. So it's like evidence against the model. So maybe that's like the way to think about it. So any questions about p-values? Okay. All right. And so this is like the formal definition. Again, don't need to memorize this, but it's good to understand all these bullet points and remember like that they're all quite important here. It is observed. It's related to a test statistic under the null hypothesis and so on. Just kind of recapping what I said. So that's a good slide to look at again too. Cool. Okay. So on to today's example. So we're going to call this A/B testing. You may have heard of A/B testing in the context of like just like tech companies like experimenting. Like every time you use an app, you're seeing something different from someone else. All these companies are running experiments on us. So we're going to do a little bit of that. And it's just really all related to the idea of like comparing two sets of numerical data. That's really what you're trying to do here, and see like, is there a difference or not? And if there is a meaningful difference, that could be important for us to act upon. And so the setup here is basically we're comparing values of individuals in some group A with values of individuals in some group B. And specifically, we're looking at numerical values here. So it's not just looking at like categories or anything like that. It's actual numerical data. And then the question we're really trying to answer is, do these two sets of data come from the same underlying distribution? Or is there a difference in the distributions? Maybe like one is higher on average, has higher values on average. And so the way we're going to do this, it's going to be pretty similar to the hypothesis test we've done so far, but there's like a few differences here. And so that's why it has like a special name, but it's really just another flavor of hypothesis testing. And so let's take a look at the data set. So we're going to read this in here. And then let's actually take a look at what this has. So for today's example, we have a data set on a bunch of babies from a hospital, and we have several variables here that we can observe about them. So we have like the weight of the baby when they were born in ounces, how many days they were in the womb, what was the age of the mother, what was the height of the mother in inches, what was the weight of the mother, this is in pounds. And then the last one, which is kind of interesting, is was the mother smoking or not? Or is the mother like a smoker or not? And so, this is from a while ago, but it's potentially interesting to look at and see if there's any differences between like categories of people within this data set. And so for today, we're going to focus on this last column, which is the smoker column, and also the birth weight, which is the first column. And so we're going to try to see basically these numerical values, the birth weights, do they differ between babies whose moms smoked and babies whose moms did not smoke? Is there any difference there? Or maybe they're the same. And that's what we're going to try to assess with this data set. So first off, let's just select those two columns because that's all we're going to really focus on for today. All these other columns also very interesting, and we might circle back to these later in the semester. But for today, we're just going to focus on those two. So let's just put them into a separate table called smoking and birth weight. And we can do this using the select function. So we just call births.select maternal smoker and birth weight. So those are just the two that we care about. And then what we can do is we can see how many people are in each category this is always kind of useful to do as in a kind of an initial exercise, just to get a sense of like how this data is distributed, basically looking at the categorical distribution of maternal smoker here. And so we can just do group on maternal smoker. And so we can see here that there's 459 mothers who smoke and then 715 who do not. So those are pretty large numbers. Like this is a sample from a hospital. And so it's those are pretty large sample sizes. And they're not the same. That's okay. We don't need them to be the same to make a comparison. But they're both large enough that we should be able to make some sort of inferences about kind of the population as a whole, potentially. And so one of the first things we might do is maybe look at the actual distribution of the weights between these two. That's one way to compare, you know, is there a difference at all? And again, this is going to be an observed difference. This is just going to be a difference within our particular sample, right? That we should expect to see some difference just by chance. But the question really ultimately is, can it be explained by chance or is it beyond chance? And so to do that, let's actually, question for you, what's the chart we should use to show the distribution of birth weights? And how could we show that for both smokers and non-smokers in one chart? What's the name of the chart? You can just say it out loud. Histogram, okay, some murmurs, histogram. All right, so yeah, let's do a histogram. So we'll do birth weight. And then I don't want to just look at the histogram of all the birth weights. I want to split it up by smoking and non-smoking. So if I just do this on its own, this isn't very interesting. It just shows me all the birth weights. But I want to actually split it out by smoker and non-smoker. So we can just add a second argument, group equals maternal smoker. And this will overlay two histograms on top of each other. And so here we see in the gold, we have a histogram of all the birth weights from the babies whose mom smoked. And then the blue is the babies whose moms did not smoke. And so you can see here that it looks like this gold histogram is like a little bit to the left, right? The bars are much higher here on this like lower end. They tend to be lower like on the right side. So it seems like if you were to compare like the average of these two, maybe that they might be different and one might be lower than another. But again, this might just be chance. We do have like a lot of people here, 459, 715, total of like more than 1,100. So it's a lot of people in our sample here. But nonetheless, we should expect some difference. Like we should expect them to be exactly the same. That would be a little bit weird, right? And so the question is really, is this chance? If we could somehow simulate from this null hypothesis that they're the same and see how often it actually moves around and see how that compares to this, what we observed, then we can make a conclusion. So similar kind of exercise we're going to go about here. So any questions so far about this example? All right. So to recap a bit, we have a random sample of mothers and their newborns. And we're trying to compare, let's say, group A, which is birth weights of babies of mothers who smoked during pregnancy, and then group B, which is birth weights of babies of mothers who did not smoke. And the question is really, could the difference between the two be due to chance alone, or is it beyond chance? And there's something else going on. And so the way to write down the hypotheses, this is going to be a little bit different than the way we've done them so far. So for the null hypothesis, we're going to say in the population, the distributions of the birth weights of the babies in the two groups are the same. And so, you know, these are like random samples from these two distributions. The distributions are essentially the same. Any differences we see in the sample just due to chance. So that's the null hypothesis. And then the alternative is that actually these are random samples, but in the population, the babies of the mothers who smoked actually weigh less than the babies of the mothers who do not smoke, on average at least. Not like every single time, but if you look at them as a group on average, you're seeing lower weights among the smoking population. So that's the alternative. So maybe a question for you. We haven't even gone over yet what the test statistic is going to be, but based on this, do you think we're going to use absolute values in our test statistic? Think about it for a second. So who thinks we're going to use absolute values here? Who thinks we're not going to use absolute values here? Okay. For somebody who said we're not going to use absolute values, why is that? Want to explain why you think that's the case? Yeah. Yeah, so our term about hypothesis is in one direction. So it's saying the babies of the mothers who smoked weigh less, right? So that's really the key here. We said weigh less, that's a particular direction. We're not saying they weigh differently on average, right? That would be a very generic statement. This is a very specific statement, weigh less. So that's a particular direction. So that should be a hint that we're probably not going to use absolute values in our test statistic. And so then the next question is, what should our test statistic be? How can we summarize our data with a single number? Any guesses? Well, actually, let's start first, maybe something simpler. So I have these two samples. If I had to summarize each sample individually with a single number, what number would you choose? Yeah. Yeah, the mean maybe, right? So take the average value of the birth weights of the smoking babies, take the average value of the birth weights of the non-smoking babies, right? So that's maybe one way you could summarize that data all into one single number for the purposes of this test. But we need to combine those two into a single number. So what could we do now? How could we combine those two into a single number? Because we got to summarize this whole data set with a single number. That's our test statistic. Any thoughts on what we should do with those two numbers? Yeah. Yeah, take the difference, right? And so this is a situation where if this said that the weights are different, maybe we'd take the difference and take the absolute value of the difference because we wouldn't really care about like whether it's positive or negative. But in this case, we're saying way less. So we want to take the difference of the two means without the absolute value, and then look at specific values. So let's say we did like the average weights of the smokers minus, or actually let's do the average weights of the non-smokers minus the average weights of the smokers. So is that going to imply that high values of that statistic are in favor of the alternative, or is it low values that are in favor of the alternative? Maybe discuss with the person next to you for like a minute. And if you didn't catch it, I said non-smokers minus smokers. So. All right, so any thoughts? Is that going to be high values for the alternative or low values for the alternative? What do you think? Yeah. And why is that? Yeah, so basically the suggestion is higher values will actually be evidence for the alternative if that's the direction we choose to do the difference. And because then you're saying that the non-smokers weigh a lot more than the smoking mom's babies. And so that kind of is in line with what the alternative is saying. And if it's the opposite direction, then it would be kind of evidence for the model in this case, because it's just evidence for one of the two. Now, it's a little bit arbitrary which one you choose. So you could do non-smokers minus smokers. You could do smokers minus non-smokers. It's really up to you. You just need to recognize like whether it's high values or low values. And so that's the most important thing. And that will then weigh in when you're calculating that p-value. So you know like which direction to look. And so the way we're going to do it is we're going to say group A is non-smokers, group B is smokers. We want the difference between the weights. So we're actually going to do group B average minus group A average. So we're going to do smokers minus non-smokers. And so it's actually the reverse. And so in this case, because we're doing the opposite direction, it's going to be low values or evidence for the alternative. So we just kind of flip the question around. I know that seems a little bit complex, but it's good to get used to like being able to do either way. So we're doing smokers minus non-smokers, and therefore like the lower this entire quantity is, then that's more evidence for the alternative. Cool. And so basically you want this to be like, if it's more negative, that's evidence for the alternative, because that's basically saying this is smaller than this one. That's the only reason this would be negative. All right, so let's go ahead and actually calculate the observed test statistic in this case. So we can go ahead and use the mean function to do this, or sorry, NP.average. And so we can do smoking and birth weight. So that's the table that has just those two columns in it. We're going to do a group again on maternal smoker, but I don't want to see the counts. I want to see the averages of the two values. And so let's go ahead and get the averages, and then let's see what they are. So we've now summarized each of these two into one number. So we know that among the non-smokers, the average birth weight is 123 ounces. And then among the smokers, the average birth weight is 113.8 ounces. And so we can go ahead now and calculate that difference. And so before you even go ahead and calculate the difference, it's a good idea to just kind of do like approximation in your mind. Like, okay, this is like 123, this is 113. So the difference should be roughly 10. It should be negative 10 because we're doing true minus false. So just kind of do that little check in your mind, and then let's go ahead and check it out. So the way to do this math really easily is we can take just the second column of that table, and then we can just subtract item 1 from item 0. So observed difference is going to be the means item 1 minus means item 0. So basically this is saying take the second row, subtract the first row. And then we can take a look at what the number is just to make sure. So we're getting something like roughly negative 10, not quite, but almost. So that seems right here. And so this is the difference that we observe here. And so happen to observe this difference seems like kind of large. I mean, minus roughly 10 and like the baseline maybe is like 100-ish, right? So it's like about 10%. So basically what we're seeing is like the babies are 10% lighter. Like that feels kind of like a lot. But again, don't really know how meaningful this is because we have to go into a simulation, right? We just observe this from our samples, but maybe that's a difference that you'd expect, even if they were actually the same in the population. We just happen to have like a subset of people that maybe they just happen to be a little bit less. So we got to figure that out. And so before we go and do that process of trying to like simulate, we should put this into a function. That's kind of what we always do. So we always try to put this into a function. So it's like very easy to calculate the difference of means for any arbitrary data set. Because we're going to go right now and like simulate a bunch of data like this. We're going to simulate a bunch of babies whose moms are smoking, a bunch of babies whose moms are not smoking, calculate the difference of means, do that again and again and again. So it's helpful to make this a function. So I already started to write this down here. It looks a little scary, but it's not too bad. So the function is going to be called difference of means because that's what we're trying to calculate. That's our test statistic in this case. And it's going to take in a table of data, maybe like our sample data or the simulated data, as well as what's the name of the numeric column and what's the name of the categorical column. So like smoking versus non-smoking. And then what's going to return is the difference of means between the two groups. So that's what this function is going to do. And it's going to basically go through the entire process of all the code we just wrote above, but it's wrapping it all into a function that we can just call again and again. And so if you were to start out with like a brand new data set, then the first step is to like just get the two columns that we care about. So we'll take table and do dot select, numeric label, category label. And then once we have just those two columns, then we're going to create a table that has the means. So we can do this just like we did it above. So we'll take just the table that has the two columns and then group them by the category label. And then make sure that we pass in np.average as a second argument. So that's going to go through the process of like group my data by the two categories and don't show me the counts, show me the average of like whatever numerical quantity I have. And then once I've done that, the last step is to extract just the averages from that table. So we're going to take the means table and just take out the second column because we know the second column is going to have the averages in it. And then finally just return the difference of the means. So means.item1 minus means.item0. So if you look above, this is the same code we just did over multiple cells. We're just putting it all into one thing here. And then the one reason that I'm making this so generic, like I'm not even mentioning smoking in this example at all. This entire function has nothing to do with smoking, is because this is a good practice to have. Like when you're writing your functions, try to make them more generic so it could work for any data set. Like if I wanted to do this same process again for like another data set, or maybe even another set of data, like let's say I wanted to compare the weights of the moms between smokers and non-smokers, I could go ahead and just swap that out really easily here. So that's why we try to make this a little bit more generic. But now we have this all into a function, and we can now run this function on any arbitrary data set, and it will just give us a difference of means. And so it's like nice and easy in one line of code now. So now if I want to do this, I can do a difference of means. I can pass in my original table, which has like all those different columns in it. And then I can just specify, okay, give me the difference of means between birth weight and maternal smoker. And it will just go ahead and do all the work for me and just calculate the difference of means in this numerical value between the two options of this category. So any questions, about how we wrote that function? Does that make sense? Okay, so we know now how to calculate a test statistic if we were given a set of simulated data. And so the question is, how do we simulate this data, right? So we have this sample of babies, and we know their weights, we know whether their mom smoked or not. They've come from some population, this like larger population of like moms who smoke and moms who don't smoke, right? And so we have to somehow simulate another set of people like this, but assuming that the distributions are the same of the weights between the two groups. So it seems a little bit complicated. Like, how would we do that? Because we can't really use the methods we've done so far. Like in the first example we ever did, we used sample proportions because we knew in the population, theoretically, it's like 75% purple and 25% white. Like that's what's being claimed. And then same for like the Alameda case, like we knew there was this like theoretical population distribution that we could just sample from. And then in the GSI case, we knew that, well, we have the entire class, like that's the population. So let's just sample from the entire population. But here we can't do that. We can't just go sample from the entire population. So it's not that straightforward. We can't just like simulate a bunch of new babies. It's not that easy here. We already have like all of our data in front of us. So we got to come up with a way to simulate this. And so one way to think about this is to consider the way that our data is actually structured here. So essentially, if you just dumb it down, like all we're seeing here is we have non-smokers and smokers, and then we have like the weights of the babies. That's pretty much what we have. And so these are sort of like their labels. It's just like, these are the categories they're in, and then these are the weights they happen to have. And so one thought here is, I have this data, maybe I could do something with the data I have to simulate under the null hypothesis that the weights are the same. And so one way to think about it is, if the null is true and the weights of the babies who are like from the smokers versus non-smokers is actually like the same on average, or the distribution is the same, then what that means is the label shouldn't even matter actually. Like if you just take away these labels, it shouldn't even make a difference anymore. Like the averages should be like roughly the same, distributions will be roughly the same. And so essentially what we could do as a way to simulate maybe is we could just shuffle all these labels around and just mix them up and then compute the difference of means again. And then mix them up again, compute the difference of means again. And that seems like it would replicate what would happen under the null, because under the null, it doesn't even matter what label you have, right? It's the distribution's the same. And so that's maybe one way we can sort of try to like get around it. And, you know, it may not be totally satisfying to hear that, but like that is actually, it turns out, a very reasonable way to simulate from the null in this case. And so just to recap again, I know it's a little bit weird, but basically, let's just keep all of the weights of the babies where they are, and let's just shuffle around the actual category that they're in. So imagine like everybody just has like a little ticket. It's like smoker or non-smoker. Let's just mix those tickets around. You still have the weight you have, but we're just mixing around like your category. That's it. And then let's compute the difference it means after that. Because if you just mix it around, like you shouldn't really observe any systematic differences between the two categories. Sometimes one will be higher, sometimes one will be lower just by chance. That's what we would want to see if this was actually like from the null simulated. And so it turns out that's a reasonable way to do it. And this is actually a test that's used often. So it's called permutation test. And it's very helpful in situations like this, where like we're trying to assess what would happen if the null is true, but we can't just go out and like sample a bunch of babies again and again, because we don't have enough money to do that. And so we can just repurpose the data we have. And so that's what we're going to end up doing. And so the process basically is going to be that we have this column of numerical values, we have this column of categories. What we want to do is just shuffle the categories. That's essentially what we want to do. So keep them all the same. That's actually really important. We want to keep like roughly 700 who are non-smoking and like 400 that are smoking. You still want to keep that breakdown, but just move the rows around. It's just like shuffling a deck of cards. That's literally all you're doing, but keep the numerical data where it is. And so we can do this in Python. We've kind of done this already. So there we have the sample function, which lets us from an entire table sample like a subset of the data just randomly, right? And then if you don't pass in a number to sample, it just takes the entire table and samples it. So whatever like number of rows you have, that's what samples it. So that's getting a little bit closer to what we're trying to do here, which is like, let's take the entire table, not just like a subset of it. And then you can also pass an argument, which is with replacement equals false. So if you do that, it's going to guarantee that you're getting everybody exactly one time. You're not like getting someone, putting them back in, and then accidentally having a chance to get them. You're just getting everybody exactly one time. And so the way we're going to do it is this very last bullet point, which is sample, don't specify the sample size because we want to get the entire table, but we should specify with replacement equals false because I want to make sure everybody comes out just one time and exactly one time. I don't want like duplicates here. And when you do it that way, you make sure that you have that same breakdown, like 700 non-smoker, 400 smokers. So let's see an example of how this actually works in action. So I have a table here that I just made up. And let's say we wanted to shuffle from this and actually like see what happens if we mix it around. So the thing that we learned like a few weeks back was just sample. So if you just call sample without anything, it shuffles the entire table, but you might have repeats when you do it like this. So in this case, notice we got Pam and Michael twice, do it again. This time we got Michael twice, so on. So this like isn't exactly what we want. We want to just like change up the order, but keep everybody exactly the same, one for one, don't want any duplicates. And so all we got to do to fix that is just do with replacement equals false, and then we'll get a unique combination every time. Actually, permutation, I should say. So we'll get a unique order of these every time. And so we're preserving like the same people that are in there. So that's what we want to do. And we essentially want to do that with like our entire table. And then in our specific case, we don't actually want to shuffle the numeric data. We want to keep that as it is. We just want to shuffle the categories. And so one way you could do that is you could take this like shuffled table, which is, it's not actually changing the original table, but just take out the column you care about. So you could just take like, for example, in this case, the names column. So let's say I wanted to keep my ages where they are, but I just want to shuffle the names. I could just do this, and this will just change up the order of the names. And that's what we're trying to do. We're just trying to change up like smoker, non-smoker. We want to keep the actual birth weights the same. And so that's like the main process that we're going to do. So now we have a way to sort of like randomly shuffle our table. And we've kind of at least sort of agreed that it seems reasonable to just shuffle around the labels as a way to simulate from the null. And so just to put it all together, basically, if the null is true, then all rearrangements of the labels are equally likely. Like it doesn't really matter what the labels are. We should be able to just shuffle them around. That seems like a reasonable way that we might generate data if we actually were to go out and sample more. And so the idea is, let's shuffle all the group labels, which is like the smoking category, assign that shuffled category to a birth weight, and then find the difference of the averages between the two groups. And then just repeat that process again and again. And so every time you do this, we should be getting slightly different results. And it basically has no dependency on actually the original setup of the data. It doesn't have any dependency on like how many people were in each category or what the weights actually were, because we're just moving stuff around here. So it actually has like no dependency at all. And this should just work. So let's go ahead and actually do this. So let's do this for like a single example. So just to recap, this is what we have. And what we're going to do is we're going to try to move around the maternal smoker stuff. We're just going to shuffle this column and keep this one the same. You don't want to move this. And so we can go ahead and do this in a similar way that we just did the prior example. So we're going to call this shuffle labels. And what we do is we take our table, we're going to sample everything inside the table with replacement equals false. So basically just means shuffle the table, and then just take out the maternal smoker column, because that's actually what we want. So let me do this over 2 lines so you can kind of see it better. So like this. So sample the entire table without replacement, and then just take the maternal smoker, because that's really what we're trying to shuffle. We're not trying to really shuffle the whole thing. And so once we do that, now we have our maternal smoker column jumbled up, and then we could create a new table, which has the original numerical values and has these new shuffled smoking categories. And so we'll do smoking and birth weight with column. So we'll just add a new column in this case. And let's just call it shuffled label. And it's just going to have these labels that we just created by shuffling. And then we can take a look at what this has. So now we'll see all of them together. So we did one run of this. We have our original smoker column, our original birth weights, and then a new set of shuffled weights, smoking category on the last end. And then we can go ahead and do this again. So like I could run these 2 lines again, and then you'll see that last column is going to change a little bit. And do it again. Last column changes a little bit. But the first 2 columns is exactly the same. All right, and that's basically what we wanted to do. We wanted to keep these where they are, move these around. And then once you've done that, now if you wanted to calculate your simulated test statistic, all we have to do is call that difference of means function on this table, but pass in the shuffled label instead of the original label. And so now this is really nice and easy to do because of that function that we made super generic. We can just pass in original and shuffled. We pass in the numerical data that we want, and then we pass in the category that we want, which in this case is shuffled labels. And we can go ahead and run this. Do this on another line so you can see it. And so here we happen to get a difference of means, also negative, but negative 1.7. So not quite as big of a difference. And then what's cool is now I can just go ahead and do this again and again. So I'll run the 3 lines again. So shuffle your data, add it to the original data, find the difference of means. Now we got positive 2.27. And so now we can just do this like all day and simulate a bunch of test statistics under the null hypothesis. And then remember the actual observed one was, we can calculate it by just passing in maternal smoker instead. This is going to be the same every time. And this is negative 9.3. So that's really what we're trying to compare now. So we have a way to simulate test statistics. We have our observed one. Now we just got to go through that process that we always do this a bunch of times, make a histogram, calculate the p-value. So any questions so far? Make sense? Cool. All right, so let's just go through the whole test. So this whole thing's called a permutation test. We're going to make yet another function just to put this all nice and easy together. And this function is not just going to calculate a test statistic, but it's also going to do the simulation and then calculate its test statistic. So just putting that all together. And so the inputs into this function are the same as the other function. Take in a set of data, take in a numeric column, a category column, and let's just go through that process. So like first step is shuffle your labels. So it's basically what we just did. So take your table, sample the entire thing with replacement equals false, and then just pull out the category label, because that's the one that we're actually trying to shuffle around. Once we've done that, we have our shuffle labels. Now we just got to stick it together with our original numeric data. And so we'll just, in this case, create a new table that has just those two. It actually doesn't really matter. But we'll create a new table that has just the original numeric data with the shuffled categories. And we'll call this shuffled label. Sorry, let me do this on multiple lines here. And it's going to have these shuffled labels. So here I'm just constructing, again, a new table that has original numeric data plus shuffled categories. And then finally, last step is calculate the test statistic from that simulated data. So at this point, we've created a simulated data set at this line. Now we just have to like calculate a test statistic from it. So we can do a difference of means, pass in our table, and then we will be having the test statistic returned to us at the very end. That should be numeric label. Oops. Oh man, that's not what I wanted. Okay. So that's the last line. So it's just like compute the test statistic. And so this is just nice and easy because now we can just run this whole thing in our simulation, because this goes through the whole process of like create our simulated data, calculate the test statistic. And so let's just make sure this is actually like doing something reasonable. So we can go ahead and actually call this function on the births data set. We're going to call it specifically with birth weight and maternal smoker. But notice how I could just swap these with any column names and simulate a bunch of data all day now. So this is really convenient. And so you can see how this is moving around. So I'll run this a few more times. So you can see the kind of values you're getting, sometimes positive, sometimes negative. So seems like we're kind of simulating under the null where they're the same. And it's not exactly the same in the sample, but it moves around a little bit. And so let's do the final step here, which is to do this many, many times. So we're going to store this in an array called differences, and then we're going to do this in a for loop like we always do. In this case, this code actually does take some time to run because it is shuffling the entire table. So we're just going to do it 2,500 times, not 10,000 times, but you're welcome to try that on your own if you want to. And then in each iteration of the for loop, we're just going to basically call this entire line of code here, generate one simulated difference of means between these two groups, assuming the null is true, and then just add that to our array of values. And then finally, at the end, we can just make a histogram. So I'll let that run. Oh, no. Let's see. New differences is not defined. This should be new difference. Okay. There we go. So we'll let that run. And then the last step is to just make a histogram of the simulated differences. So let's just call this simulated differences. And it's going to have all the differences we're calculating here. It's still running, taking some time. And then we'll just do a histogram of that. Wow, it's still running. That is weird. Okay, well, we'll let this go. That is strange. Okay. And then once we have our histogram, then we basically need to calculate our p-value, which is like what % of the data lies beyond the histogram. But first off, here's our histogram. So simulated differences here. So again, what is this showing us? This is saying we assumed that these two populations were the same in the population. The distributions of the birth weights were the same. And so we like randomly sampled a bunch of babies whose mom smoked, a bunch of babies whose moms didn't smoke. And then we just compute the difference of means. And we did that like 10,000 times or 2,500 times in this case. And these are the kind of differences we saw. So like on average, the difference was 0. That's what we should expect because that was the whole point of this. The whole point of this was to simulate what happens when they are exactly the same. So you should expect that it's centered at 0. That's totally reasonable. That's nothing wrong there. But what we're trying to gauge is how far does this go out? How often does the difference get really, really large? That's what we're trying to understand. And it turns out the difference never really gets beyond 2 in either direction. But remember, our difference was like -9. So our difference is really, really large relative to this. So our difference is like way, way over here. It's like completely off the histogram, off the chart. And then we talked about how low values is evidence for the alternative. So we want to see what % of the histogram lies even more negative, or sorry, for you guys, it's like this. So even more negative than -9. But you don't even really need to do the math here. You can probably guess it's going to be 0. The p-value is going to be 0 in this case because there is no part of the histogram that's going to go out that far. It's basically stopping at -4 and not going beyond that. But if you wanted, you could go through the exercise and like see how many are actually less than -9. But that's kind of the result of the test here. So in this case, p-value is going to be 0. And so we're going to conclude that the data is consistent with the alternative, which is that the babies of the smokers weigh less than the babies of the non-smokers in the population. We can actually make that kind of conclusion now. Or at least the data is consistent with that conclusion, I should say. And so that's kind of the result of the test. So any questions about that exercise? Yeah. Oh, how we computed the p-value? Yeah, so well, let me bring the observed difference. So here's our observed difference. It's -9.266. And so what we need to do is this value -9.266, it's going to be some dot like way over here. Like if I wanted, I could plot the dot, but it's going to be like way off. And then we talked about this in the beginning that like the way we chose this test statistic, we said that low values are evidence for the alternative. So like to the left is evidence for the alternative. And so therefore, what I need to do is to calculate the p-value, I need to know what % of the histogram is to the left of what I observed. And so we could actually go through the exercise. Another way to do it, which is different than what we talked about last time, is we could just take our entire table of simulated statistics, and then we could say, find all the values where the simulated differences are dot below this observed difference. Actually, looks like we already put it in a name. So we could just go ahead and do that and say, give me all of the rows where our simulation had a difference that's below -9.266. And then let's just figure out how many there are. And so in this case, we get 0. So there's 0 simulations. If you wanted to get this to a percentage, you would take the number that are below 0 and divide it by how many simulations you ran, which is 2,500. So this would get you a number, but we know this is also going to be 0 at this point. But this gives you like an actual percentage or proportion, I should say. But you can calculate this for any value. Like let's say our observed difference was like -2. We could just put this as -2, and then this would give us 3.8% as our p-value. So that's how we can calculate p-value. But yeah, in this case, it's just like so low what we observed that there's nothing in the simulation that's going to be lower than what we got. So what we got is very rare. Therefore, what we got is probably not consistent with the assumption that they're the same in the population. It's actually lower. So that's kind of the conclusion of the test. A question for you guys, based on this, can we conclude that smoking causes the babies to weigh less? Who thinks it implies that based on our analysis right now? And who thinks it doesn't imply that? Okay, and someone who thinks it doesn't imply that, why is that? Why can't we conclude this? Yeah, so it shows maybe there's like an association, but not really causal. And why is that though? Why can't we conclude causality? Yeah, so there could be some other factor, right? And it really boils down to the fact that this was an observed sample. Like we didn't go to the mothers, and you can't really do this, but like we didn't say like, hey, you go smoke for a year, you go don't smoke for a year. Like that's what you would have to do actually to determine causality, which is like obviously not ethical. But in this case, we just went and like observed what they happened to do. And so, you know, there's a lot of things that their entire life led up to that decision. There's all these other factors that could then also happen to be associated with having a lower birth. Like maybe if you live in the city versus a suburb, you're more likely to smoke. And then also, if you live in the city, you're more likely to not have like fresh food because everything's like processed food or something. And that leads to like the babies being weighing less. Like maybe it's a completely different thing, but just happen to be related, right? We don't know. We have to actually randomly assign. And so that's what we're going to do on Monday. We're going to do this exact same exercise, but in a situation where you've randomly assigned. And what we'll find is we can actually conclude causality. This is how we can actually show whether something causes something else. So it's gonna be pretty cool, but it's all around under this framework of A/B testing. Sweet. All right, so we'll stop there and we'll do causality on Monday. Sweet.